welcome in for AML Conversations. My name is Vladimir Ermin, and along with Kieran
So my name is Koen Duterloanje, if you want to pronounce it correctly. But I accept anything. Koen is fine.
Yeah, we're going to be a host here for this event. And how many of you guys here is first time? Ooh, almost everyone. A lot of people who, I saw a few people who saw previously, but they also like raise their hand, but that's okay. Anyway, so I think it's worth to tell a few words about what's AML Conversations. Besides from the name that you probably guess it's about ML and AI, and you're right. One thing is that this meetup, born as just a few friends meeting over the beer and some non-alcoholic drinks, and we were talking about like our daily lives as doing like machine learning, and it was always like a really good, and I learned so many new approaches to how to apply AI. I'll remove this possible that I don't know. And it was so good that me and my friends, we decided, okay, we want to bring this to the stage. We want to kind of get the opportunity for those people to speak out and share the knowledge, and in general to kind of bring reach between the industry and the science and general public, or like within the industry, within the science. So ideally to like share as much knowledge as possible. And that's how our meetup was born, and it's been a year and a half almost. And we want to kind of keep doing the same thing in terms of we are centered around our community, and the people who speak here as are just people who work in the industry and want to share their experience and knowledge. So that's the central here. And if you're for the one who first time here, you welcome and encourage everyone who wants to speak, have something to share. Doesn't matter if like you work in a startup, big tech, anything that touches machine learning, data science, or AI field in general. Please, this link will lead you to their Google form, and we encourage everyone. Even if you don't have experience talking, we can help on navigating through slides or like whatever help that you need. So our community and the values that we bring kind of goes from you. So we have a code of conduct. We probably want to put it on our website as well, but right now it's only Endure NYC, and this which means that even though this meetup is informal, yet professional, so please be respectful to each other and be kind to each other. And if you feel uncomfortable or if you experience something wrong, please reach out to us and we will take actions. Stay in touch. We have our Discord channel. It's linked. May probably not work from the screen, but please join there. We discuss there like the topics that we want to bring to our next event, or we also like meet online, and I'll have an announcement for our next working session that's gonna happen next week on Tuesday, I believe. So that's a good way to be social with us. So feel free to join. Also, here's a lot of like hiring announcements this time. Our partners are hiring for machine learning engineering. So if you're the one who's looking for a job as a machine learning or so yeah, please scan this link or ask me directly. I'll get into more details. There's someone who asks for scrolls. Here's the link, and if you find us on Supermomas, you probably want to scan this link. It will give you some bonus points, and I don't know how you can use them. Anyway, we also have this printed out.
While they're fixing technical stuff, I'll talk about Capital One. So you're in the Capital One office. I work for Capital One. The entire thing is sponsored by Capital One. They're not doing this for free for nothing. They want you to work for Capital One. So we have a lot of open positions at Capital One. So if you're interested in becoming an AI ML engineer at Capital One, or full stack, or any other role, have a look at the careers page. There's printouts with a QR code all over the place. Also, you can ask me during the break or any time. Just scan the QR code, and there's instructions on how to find jobs at Capital One and how to apply for them. We can help you with the referral process and anything that you might want to know about working at Capital One. We find it a great place, and I find it a great place to work. I hope maybe someday you find as well. So I want to thank also the co-organizers, so Weber, who is helping with the audience setups. You're on. When it works.
We really want to record this video.
And also Maria for setting up the room and everything. So it's all from Capital One.
Anyway, while we were waiting, a few questions. Anyone following this 12 days of OpenAI here? Few of them, okay. Then if you don't know the OpenAI right now, rolling out a big sort of marketing-ish campaign, and you stay there releasing a new product, I believe, or sharing about the new features. So if you have a chance, find their YouTube channel. It's I think it's more. Sorry.
Can you just show it?
I'm afraid of touching anything right now. Okay, sorry again for this delay. Every time you kind of think that you covered everything, and you put a long checklist to check everything that is done until something new happens. So anyway, a few more announcements before we start. Next week we're gonna have an online working session on a multimodal building multimodal from pre-train, and it will be run by Shafiq, who is our Shafiq is here. It's our speaker and member of our community. So please join us on Discord. I'll also post it on Meetup and everywhere. So yeah. That being said, I want to pass the mic and the stage to our guests, and Steve Carrow and Olga Vilenskaia from IBM. And it's the second time they're here. If anyone been on November, it was November? October 2023. It's still. Anyway, but yeah. I think while we're waiting, I want to ask you guys, what's the name of your talk?
What's the name of my talk?
Yeah, what are we going to talk about today?
We're going to talk about some research that we've been doing with a few colleagues of ours. At IBM. Into a new Neuro-Symbolic approach called Neuro-Reasoning Networks.
Neuro-reasoning networks. I heard about LLMs and ChatGPT. Is it related to that?
It could be. It's kind of a different direction of research than transformers, deep learning, kind of what we have come to know about how to scale up AI. And we'll obviously talk about this a bit in the talk, but it can probably complement what LLMs and deep learning are able to do, because it's actually aiming to solve somewhat of a different problem in AI than deep learning has tried to solve over these past few decades.
What problem Neuro-Symbolic AI can solve that LLMs might be struggling?
These are mostly maybe questions about like logic, reasoning, exact calculations, or exactly like the missing puzzle for Carrow architectures potentially.
Anyone heard about Neuro-Symbolic AI, by the way? Right, you. Okay. That's why I like my audience set because ask some kind of random question and people, yeah, we know that. Like that's kind of boring. So go. You have a good start.
Recording in progress.
Yes, it is. All right. The stage is yours.
Hi everyone, I'm Olga.
I'm Steve.
Today we're excited to tell you about neural reasoning networks. This is our research work accepted to AAAI 2025. So neural reasoning networks is an approach within a broader framework named Neuro-Symbolic AI, as Vlad just mentioned. So to set the stage, we will provide you an intuitive high-level overview of NSAI, or Neuro-Symbolic AI, what it is, how it is different from traditional AI, and how it intersects and complements traditional AI. Following this, Steve will tell you about the core of our paper, and we will conclude with discussion of key results. As you know, traditional neural networks draw their inspiration from the functioning of the human brain. So let's revisit a simplified model of the brain. The brain can be broadly divided into two hemispheres. The right hemisphere is responsible for things like perception, intuition, approximation, creativity, imagination, while the left brain is responsible for things like logic, reasoning, planning, analytics, computations, etc. And the two sides collaborate together to solve problems effectively, even though they specialize on different cognitive processes. For example, imagine that you need to find the shortest path from point A to point B on a map. To begin with, your right brain would provide a quick approximation, something like one of these 5 routes seems to be optimal. Following this, your left brain would perform exact calculations of all these 5 routes to find an optimal answer. So the two do collaborate to solve the problem effectively. What is the analogy of this in artificial intelligence? Deep learning seems to very much resemble the functioning of the right brain. It can provide quick approximation very effectively, though it struggles with exact calculations, reasoning, structured logic, and things like this. So it raises the question, what is the missing piece? What is this missing component which can provide this logic and reasoning and exact calculations? So let me provide you another real-life example. Imagine a self-driving car on an intersection. And the question is, who has the right of priority in this situation? Of course, to begin with, you need to get this perception of all the objects around. Like there is a red car, there is a blue van, there is a stop sign. But then some logic is needed, like who can go first? And this is potentially something you don't want to learn from data. You may want to learn from data, but at the very least, this logic should be visible and understandable to humans. Also, it would be nice to have control over it, to set potentially some constraints over it, and to have a capability to incorporate some domain knowledge. Like, for example, in this case, it would be just traffic laws, right? So now I hope I provide you some intuition why incorporating some logic and reasoning into traditional AI systems may be essential for real-life applications. And this is the area that Neuro-Symbolic AI is focusing on. So what is an SAI? It's a combination of deep learning and logic, or like reasoning. The goals of an SAI are learning with less data, generalizing far from training data, providing transparency, explainability, and as well as capability to incorporate some domain knowledge we may have. So an SAI is not a new topic. It has been around for decades, but similar to traditional neural nets, it experienced fluctuation popularity, and currently there is increasing interest and attention from big tech companies and startups alike, and companies exploring reasoning models, demonstrating the growing trend towards incorporating logic and reasoning into AI systems. With this, I'll pass it over to Steve to speak about neural reasoning networks.
Thank you, Olga. So yeah, we're going to talk a little bit about neural reasoning networks, which, as we mentioned, are a neuro-symbolic framework that we've been working on at IBM. And you can see a diagram of a neural reasoning network here. We're going to go into more of the details later in the presentation. But essentially, these are neural networks that are made up of a few new types of neurons that you may not have heard of. So we have predicates, conjunctions, which is just an AND operation, and disjunctions, which is an OR operation. And these neurons are each going to be modeling those logical operations using a fuzzy logic activation function. It gets pretty technical, but this is called modified Lukashevitz logic. And it's a weighted logic that essentially estimates those operations in a neural manner. And we get some pretty neat things from NRM. We can automatically provide textual explanations for the predictions that the network is making. And it's also implemented with PyTorch, meaning that we get GPU scaling, we get batch training, we're leveraging autograph. So this is basically embedded into our modern day deep learning frameworks and can integrate seamlessly with those. Okay, so we, in our work, compared NRM against a number of different state-of-the-art algorithms. And the comparison here is really along not so much performance, but the other qualities that we're looking for in an Neuro-Symbolic algorithm. And namely, this is looking at how explainable is the algorithm. So there's a lot of different ways that you can define explainability for an AI algorithm. We chose to go with this definition from Cynthia Rudin. She wrote a paper in Nature Machine Intelligence that's been cited over 7,600 times. It's pretty much, at this point, the de facto explanation for how you would describe XAI algorithm. And what she pointed out is that we want 3 different conditions to be true about our algorithm. The first is logical conditions, meaning we want to build our system based on rules like if then, and operations, or operations. Clearly, NRM satisfies this, that's what it's based on. Linear scoring is the second component. This is really aimed at helping us understand what's going on inside of the network. So by using linear weights, we can easily understand how different parts of the network or algorithm are contributing to the predictions that are made. And case-based reasoning is essentially the quality where we want to be able to explain the exact reason why any prediction is made in some easily understood format. So we can see that our NRM, which we'll describe a little bit later, which is our learning algorithm using the NRM architecture, actually satisfies all 3 of these different criteria. It's the only algorithm that is in the set that we compared against, at least, that does satisfy all three. And we looked at state-of-the-art explainable algorithms that have been recently developed. We looked at neural interpretable algorithms. We looked at neural algorithms that were recently developed for tabular data. And of course, their state-of-the-art algorithms, random forest, gradient boosting, and XGBoost. So it's pretty neat that we get this high level of explainability. Now, let's talk a little bit more about NRN itself. So I'm going to break apart this diagram for us. Neural reasoning networks are very much like neural networks, except that, like I mentioned, each node is representing a specific logical operation. And so we're going to construct these networks out of layers of conjunction and disjunction nodes. So we can see here the conjunction is kind of the upside down V symbol, disjunction is the V symbol. And we're just going to construct our network much like MLP, just of these alternating layers of conjunction and disjunction. We will decide up front, just like in a neural network, how many layers there are, how wide are those layers, meaning how many nodes are in each layer. And that's going to kind of initialize the structure of our network. We're also going to do something that is a little bit different from a traditional neural network, which is to decide on some hyperparameters that control the sparsity of the connections. And this is basically because you can imagine if we had a lot of features, and these, let's just say, are all Boolean features, and you took a conjunction, meaning an AND of many, many features, that's always going to be false. It's very unlikely that the sample in your data is going to have all true values. So it doesn't provide much benefit to have a fully connected network when we're constructing an NRN. The last node type is the predicate here, which is always going to be the input layer. And we can basically think of predicates as features. They do a few things for the NRN in terms of explaining the predictions, but essentially these are features that are going into the system. And just like a normal neural network, all the features are going to come in as numeric values. The only difference is that they're all going to be between 0 and 1, which represents basically how true that feature is.
Just a question. Is it ideological statement where true or false with 0 and 1? It's from 0 to 1.
Yeah, exactly. So that's a good question. This is not classical logic, meaning we can take on values that are not 0 or 1. So it's a fuzzy logic. You can each node in this network is going to output a confidence score as to how true the logic is for that particular node. So you may get 50% true, you may get 100% true, depending on the data coming into that node.
And now a question, conjunction and disjunction, in your case, what is the function of there? It's like must mean or maybe something else? How do you do it?
So weighted Lukashevitz logic is a little complex. We have a slide. Okay. We don't have a slide in this
It's like
presentation.
our last year presentation. So
It's in the paper. It's in last year's presentation. It's a little complex, but it's kind of looks honestly just like a dot product. There's some other things going on that allow for that activation function to represent conjunction or disjunction, but the main workhorse of that activation function and each node is a dot product.
Steve, could you talk about a real quick note about what conjunction and disjunction is?
What they are?
Yeah, just
Oh yeah, sure. So again, conjunction is an AND operation. So it's, if we have several different, let's say, facts about a sample or, situation, then the conjunction operation is going to inspect those. And if all of them are true, then it returns true. If one of them is false, then it should return false. In our case, something less than completely true. And then disjunction is an OR operation. So we only need one of the incoming, of the inputs to that node to be true in order for that node's output to be true.
I don't know if you've looked into the neuroscience side of this.
Mhm.
If there are neural nodes that looks like disjunctions, numbers of disjunctions.
Uh-huh.
I'm kind of wondering where there is like a biological inspiration for this network.
Yeah, I don't know if these have been discovered at neuron level in the brain, but if we think about how humans kind of reason over information, we're using this type of framework, right? We're assessing if certain things are true or if they're not true, and how that plays out in terms of the deductions that we might make about a situation. So we use logic in our own decision-making kind of capabilities. It may be collections of neurons, I don't know. I'm not really familiar with that. But yeah, it would be pretty interesting to know that.
So from this diagram, so each layer seems like to have same type of operation. So does it mean that the type of operation that you design would decide how deep your network is?
Yeah, that's a great question, and it's kind of a lead into how we're going to train this system. So the question was, each layer here seems to have the same type of operation. You can see it's a layer of conjunctions, a layer of disjunctions. They're feeding into each other. And so, how does this actually turn into the logic that we want to extract from our data? And the first thing to note, and we'll go into the next slide right after this, but each of the edges here is a weight, right? So it's just like a neural network. There's a weight that decides how important is that input to the particular node. And we're going to train those weights throughout the learning process to dramatically alter the actual logic that's encoded inside of this network.
And the most common neural networks would be 2 layers.
You can decide as many or as few layers as is needed for your problem. It's a hyperparameter, just like in traditional. Yeah.
So actually, initially we set up the architecture which is the largest possible. So you set up the maximum number of layers you're going to have, and initially they're alternating conjunction and disjunction, as you see here. Here you just see 2 layers. Potentially you can set as many as you want, and always alternating conjunction and disjunction. But then we will show it, demonstrate it later, how some layers may collapse. And so actually the final architecture, it will be less than the initial largest one, or maybe less, or maybe as large as the initial one. But some layers or some nodes may be collapsed, so you may end up with completely different structure ultimately. And we achieve this structure via reinforcement algorithm that Steve is going to tell about.
All right, so yeah, let's get into how we're going to learn the actual logic or induce the logic from our data that we need in order to make predictions about new samples. So bandit reinforced NRN is the algorithm that we developed to basically perform learning over an NRN architecture. And it works by combining a multi-armed bandit with gradient descent. And these 2 components are going to work together to jointly learn the structure of that network, as well as all of the weights within the network, which determine how important is each input to each node. And the way that works is that we're going to first initialize our network. So we decide on the number of layers, we decide on the width of the network, all these things. And we're also going to initialize a multi-armed bandit policy over the predicates. And we just initialize this policy with the maximal information coefficient between each feature and our target. So it gives us some quick approximation of how important is that predicate to making our prediction. Then we're going to perform some gradient descent. And this is, like I mentioned, going to update the weights within the network. And this should hopefully improve our loss a little bit. And as the loss improves, we're going to send the weights that we get on each of those predicates to our bandits policy as rewards. So higher weights mean that that predicate is more important, which means that we should reward our bandit for using that predicate in the future. And we're going to continue that process until our loss plateaus. And then once our loss plateaus, we're going to go through this sequence of actions here. We're going to inspect our network, look at the weights within the network, and prune out all of the logic that's below some threshold of weights. And so this is going to basically prune out all of the unimportant parts of the logical network. Then we're going to sample from our bandits policy to basically fill in those pruned areas of the network with new predicates that will help us to make better predictions on the next iteration. And we're just going to repeat this process. It's going to continue for a preset number of epochs, or if you have some kind of convergence criteria, you can stop based on whatever criteria that you would like.
Can you clarify? So you have a model. The model has as output, I assume, the probabilities of choosing the arms of bandedness. Yes, so which are the probabilities? Yes. What's the input for your model, and what's the output? That's the question.
The input for the model overall.
Yeah.
So let's just say that it's like tabular classification. That's the scenario that we were working with in this particular paper. So yeah, your input is a table of data. Your output is, let's say, binary target.
Just long-term, but I mean, if you modeling the policy, the output should be which arm you use and the probability.
Oh, the output of the bandit.
Yeah.
Okay. Yeah, so the question is about what's kind of the function of the bandit in this algorithm. So here. So this policy here is over the predicates. The predicates we can think of as essentially our features. And so the bandit's policy is modeling essentially something like feature importance. How useful is this feature for making predictions within the logic that's encoded in the network? And so the bandit is going to learn which features it should be using to generate new logic that helps us make better predictions on the next iteration. So the output of this policy is actually a distribution over feature selection, essentially. Make sense? Okay. All right, so here's the results of our experiments, and we did a pretty extensive experiment here with 22 different tabular classification data sets. These were taken from a benchmark not developed by us, but a benchmark that aimed to select open source data sets that were very similar to what we would see in practice across different industries. And we performed a 400 trial hyperparameter optimization for every one of these algorithms. So we're essentially seeing, what is the best possible result that you can get from each of these algorithms. And what we found is that RNRN is on par with state-of-the-art methods, so random forest, XGBoost, gradient boosted trees. You can see p-values of a Mann-Whitney U-test here, and they're all well above 0.05 or whatever statistical significance you want to leverage there. But this is showing that essentially, the performance of RNRN in terms of predictive accuracy is very similar to these tree-based ensembles. I will note it's not an ensemble itself, it's just a single network. And some other benefits are that it's 43% faster in terms of training time when compared to some other recent neural interpretable methods and neural methods that were developed specifically for tabular learning. And it also has much fewer parameters. So these parameter counts, I know it's not listed here, but in the caption in the paper it's described, these are all in thousands. So the average RNRN has 1,000 parameters. We can see some other, pretty good recent neural methods have something like 861,000 parameters. So it's a much more compact representation that we learned with an RNRN compared to typical deep learning. All right, so as I mentioned, one of the main objectives of developing neurosymbolic systems, and especially RNRN, was to be able to produce explanations that are useful to us as practitioners, to us as end users of algorithms. And we can see an example of an explanation produced by a trained RNRN algorithm. And this is on the California housing data set. I don't know if everyone is familiar with this. It's basically you're trying to predict if the price of a house is going to be above or below the median price. And you use features like the number of rooms, the number of bedrooms, the median income in a specific location, the location itself. And what we can see here are just two randomly selected examples of sample level explanations. So these are the explanations for a particular sample in the data set. And we can see for the positive class and the negative class that the values actually differ in ways that we might expect, right? So in the positive class, there are typically more rooms. We have up to 7 versus up to 4. It's a newer construction, and this is a little bit blocked, but the positive class has higher median income, 33rd to 38th percentile versus 11th to 14th. So these are very intuitive kind of reasons that we might expect a house's price to be above the median versus below the median. And one of the really neat things I think about these explanations as a practitioner is that as you're developing your algorithm and you're training it, you can actually leverage these explanations to debug it. You can see, is it learning some strange relationship that I don't want to encode in my model? You can basically have a lot of visibility into what is going on. You can spot different data errors very easily. And of course, when we actually put these models into practice, having that explanation, the reason why a prediction is made, is going to help with adoption from end users. Now we're going to describe how we actually generate those explanations. And to do so, we're going to inspect the exact structure of the model that was learned through the training process. Every explanation is a one-to-one mapping with the representation that was learned by the model. And to do so, we're going to simply do a depth-first traversal over the network, where as we traverse this network, we are going to inspect the weights that were learned throughout the training process, and then essentially skip over the parts of the network that have very low weights, meaning that they don't contribute meaningfully to the output of a particular node. And so as we do this, we're essentially extracting the logic that was induced during the training process, and we're going to be able to automatically generate textual explanations with all of those rules that you saw on the previous page. And one other thing that I find compelling about this is that we not only get something like which features were used to make a prediction, we actually know what are the specific values of features that were required for that prediction to be made about a specific sample. So there's a lot of information in these explanations that we're able to automatically extract with this simple traversal algorithm. So now I'm going to pass it off to Olga to explain the remainder of explanation generation.
Okay. As we mentioned, the original model that you set up in the beginning, it can appear to be pretty complicated. So the model that we end up with may be pretty complicated. So I'd like to demonstrate to you how the simplification process works. So here you can see some nodes, they have negations like not, or, not, and, not predicate. Basically, it means that the corresponding weight was negative. So negative weight means that we need to negate the corresponding node. For simplicity, I decided not to show weights here, but show negation this way. So for first thing in our simplification algorithm, we would push the negations down to the leaves, starting from the top leaf that has negated node, for example. sorry, not from the top leaf, top node, which has a negation. In this particular case, we start with this not for, and we will apply logical rules for it. For example, in this particular case, the logical rule would be not or of A and B is equal to and of not A, not B. It's just logic, right? So we applied to this particular node the closest one to the root, which has negation. So in this case, not or will be changed to and will become not and not and will become not and. We will get something like this. Okay, so this is the equivalent model. Okay, now we see not and, double negation, we will get rid of them along the way. It's easy, obvious rule. Okay, now this is our new model. We will repeat the same for the next node, which has negation and the closest one to the root, which is not or. We apply the same rule again. Not or will become and will become not and. So this is the new model. Okay, now we repeat the same procedure again to the next node, the highest one, which is negated. This is a similar rule, but with not and of A and B is equal to or of not A, not B. So not and will become or, not P1 will become not P1, P2 will become not P2. So this. Again, we will get rid of double negation. This is our model. Okay, we repeat the same for this node as well. Same procedure. Again, we get rid of double negations. Okay, this is our model so far. It still has the same number of layers, but all the negations that we have can now only be on the leaves. We don't have any negations on internal node at this moment. And as you can see, it already may not necessarily be alternating conjunction and disjunctions. These types of nodes may already be changed a little bit. Now we keep applying some other logical simplification rules. For example, here, end is just end, so we will collapse consecutive conjunctions or disjunctions. It will become just end node, and then here, obviously, end of A is A, or of A is A, so whenever there is just a single child, we will also collapse those. So this is our current network. Okay, now there could be the case that we can simplify it even further. Imagine for a second that these two predicates are the same. We can have the same feature appearing multiple times there because of the process that Steve described, like how we pick this, how we choose these predicates from a distribution. So it may appear that some of these predicates are the same. And imagine for a second that both of these appear to be D1. Okay, then we may be able to apply a more complicated rule. So look at it for a second and you'll understand. If we have and of for A, B, and A, it means that we require that A is true. So this whole and thing is true only if A is true. But if A is true, then we don't need or of A and B. We don't need any information about B because we already know that A is true. So this whole thing is actually just A. And if we're here to have these predicates twice, then this could be just simplified to this. I hope it was clear, but
It's clear, like for traditional logic, it's not clear, like for fuzzy logic, like how or and define it. Will it work like this?
We have some threshold, so like beyond this threshold, we consider it to be true, or like below some particular threshold, we consider it to be false. So we kind of convert fuzzy logic into true false, but this is a good question.
Yeah, it's a good question, and the whole network is fuzzy logic, right? So if you, even on those explanations, there's a weight associated to each of those logical operations. And so you can inspect that level of information from the network to see what is the actual weight for this operation. Of course, that makes it harder to interpret as an end user. So it's a trade-off. You can get that level of information at the cost of having more complex explanations.
The definitions of a fuzzy or fuzzy end, they are present in the paper, right?
Okay, so
Follow-up question. Can the threshold of this logic be a hyperparameter itself, or it's predefined?
Yeah, you can define whatever threshold you want to kind of convert your logic from fuzzy into, that classical form. Whatever level of confidence you decide means that you've actually discovered a true logical operation.
okay, so in some cases, it can be simplified even further. We have the whole simplification algorithm in the paper. It's much more complicated than that. I just wanted to provide you some intuition how the model can be significantly simplified with just applying logical rules. So now, even if we don't have the same predicate here, this is our simplified model, our final tree, and you can see it's already much simpler than the initial tree. And I want to stress out here that this is not an approximation. This is exactly the same model. So it's exactly correct. Yep.
So the score will not go up the simplification.
We apply the simplification to, we don't do it inside the training. We only apply it to the final model. So once we have final model, which says, if you have number of rooms more than that, and this and this and that.
Just as like the original model and the simplified model, I mean, after, like their performance stays the same.
This is the same model. There is like no difference.
Yeah, so we're not simplifying the model during the training process, like Olga mentioned. So whatever was induced from the data is going to be that more complex structure, the initial tree. We're only doing a simplification during the explanation generation. So when you want to know why was, this particular prediction made, we run through this simplification process. Does that answer your question?
I think so. One more question.
So the question is related. What's happening if you apply this simplified network giving inference? So you say that the network is the same, no? So you are reducing the inductive capabilities, or you achieve the same result?
It's a really interesting question. It's something that we've thought about because I think what you're pointing out, what you're both pointing out, is that you can potentially represent the network in an even smaller, more compact way.
Yeah.
And if it achieves the same level of performance, perfect. We haven't done that experiment. I think it's a really interesting question that you ask, and would be worth looking into.
It's somewhat contradictory because you say that it's the same network, no? But actually, it seems like a deterministic process, but this is not a deterministic process. It depends on the threshold that you set, to switch from fuzzy to true logic. So this kind of step is not deterministic.
Okay, sorry, maybe I need to clarify what I meant. Maybe I need to take my words back. So what I meant is that in terms of explanation, it's exactly the same explanation that you would get, like you would get this long explanation, for example, why some particular sample belongs to this class. You can create this explanation because it has more than 3 rooms, etc., etc. And in terms of this explanation, much smaller one, will be exactly the same explanation. It does not imply like the same weights or model. Like in terms of explanation, it's exactly the same explanation, just much more simplified.
Same logic, not same model.
Yeah.
Thank you.
Yeah.
That's a great question.
Yeah. And sorry about the confusing faced before.
You have tree on deck here. It's important. You have a tree explanation, or you have a deck-like structure. Direct density graph.
It's a DAG.
Deck.
But
We represent that here is a tree, just for simplicity.
But even there, you can represent it as a tree. You can kind of split the same node into multiple nodes, and it will end up being like.
Yeah, I understand, but it can be very explosive. For example, if you take sort of multiple arguments and you try to represent it like a tree, it will be exponential in terms of size to explain such function. So this I must.
It's implemented as a DAG. Yeah.
Okay, so we stopped here. That this was our simplification step. Now, going further, let's from this model, let's see how we create explanation for a particular sample. So for a particular sample, not all of these predicates may be true. For example, as you see in this model, we can have P1 or not P2 for the model to be true. And for a particular sample, we are going to ignore everything which is not true. For example, let's say for a particular sample, this P1 is not true, we just ignore it. So it will become the model for a particular sample. So, and as you can see, since everything that we leave in the model is true, we can say it's just single layer conjunction. We can get rid of all the disjunctions because everything that we left in the explanation is true. Everything which is not true, we just ignore it. So sample level explanation is guaranteed to be a one layer conjunction always. It's always end of some predicates. And this example that Steve showed before, it's not a coincidence that you see this explanation, all of the following at all. It's not like an approximation, it's exactly the model applied to this particular sample. And this is like, as opposed to Shep or Lime or some other approaches which try to linearly approximate some very complicated, like nonlinear model. This is not an approximation. This is exactly the explanation, the whole explanation for the sample. Okay, now let me speak about how we generate feature importances. So as we mentioned, each edge in this graph has a weight. We calculate product of observed weights along each branch to get aggregated weight for a particular leaf. And then we just sum up all the aggregated weights for the predicates in which particular feature participates. And that's it. That's how we define feature importance. Now we need to check how good the feature importance is. So this is the explanation quality. We measure it in terms of three parameters: compactness, correctness, and time to compute it. So size is a good measure of compactness. Smaller explanations are easier and to understand, obviously better. Size here means number of features mentioned in the explanation. Then how we measure correctness. This is a bit tricky. We apply single deletion correlation. So let me explain to you what it is. The intuition is that imagine that you remove one feature from your model. If the performance dropped significantly, it probably means this feature wasn't good. If it did not change much, probably this feature wasn't very important. So what we do is we choose one feature, we randomly shuffle its values, and we create predictions for those modified data set. And we see how accurate the predictions are. So we compare the performance of on the original data set versus this modified data set when one feature value was shuffled. And if the performance did not drop significantly when we shuffle the feature values, it probably means this feature wasn't very important. If it drops significantly, it means that the feature was important. So that's why we measure a correlation between this change in performance and the value of this feature importance that we calculated before. And so this SD Spearman and SD Pearson, they mean single deletion Spearman correlation and single deletion Pearson correlation. Obviously, the larger the better. And as you can see here, only SHAP for random forest and only for Pearson correlation is better than RNRN, but SHAP takes more than 20 times longer to calculate than RNRN. RNRN takes about 4% of the time to create explanations in comparison with SHAP for random forest. So from this, we conclude that our explanations are small in size, on average more correct, and take much less time to calculate. And this is the end of our talk. These are some resources, links to our paper, to our presentation from the last year, which has a little bit more information about Lukashevich logic, some formulas. And also, if you're interested in Neuro-Symbolic AI in general, there are a few summer schools, and you can see a bunch of those there. Thank you.
Thank you. I think we can take some questions from audience. I know you can ask more questions.
Well, first of all, thank you for this amazing work. We are colleagues and working for APM. So, general question is about how this model is robust against adversarial attack. For example, the noise. If you had some error analysis on this kind of topic.
Yeah. Unfortunately, we don't have that in the presentation. It is in our paper. So we did a couple different experiments to see how robust it was across different types of noise. So one of them was basically a label flipping experiment. So we take some data, we generate, a synthetic data set for classification, and then in our training and validation data, we flip some percentage of the target. And then we just do an inflation study to see, as you flip more and more of the target, what's the drop in performance. So I think I might mess these numbers up, but when you don't do any label flipping on this particular data set, we were getting something like 95 AUC, let's say. We can go all the way up to 40% label flipping and only get a drop down to, I think, 91 or 92 AUC. At 50% flipping, you're erasing all information for the task that we did this experiment on because it was binary classification, and you see the AUC drop down to random. So essentially, it's very robust to label noise. We also looked at feature noise. So what happens if you just add thousands of irrelevant features, right? And so in this study, we did a very similar thing, except that the change from iteration to iteration is just how many irrelevant features do you have. I think we went up to 1,000 or 10,000 irrelevant features and saw no change in AUC. So it's robust also to kind of feature noise. And then the last experiment that we did was basically to do a similar thing where we add irrelevant features, and then we want to see how well does the algorithm recover the few important features that are remaining in the data. And using our feature importance, we found that when you go up to, I think it was again, either 1,000 or 10,000 irrelevant features, your top 3 features are still having at least one of your 2 important features among that entire set.
This is great, thank you. And I have about the explanation. When you generate text for the explanation, you are not using any generative AI here and language model. You are just navigating the topology, and you use the name of the features. You concatenate them somehow.
Yep, exactly. Yeah, that's one of the things that's within that predicate node. There's a bunch of functionality to produce these explanations. One of them is a mapping to the name that you want to represent within the explanation. we just use that.
If this feature like cryptic name, if cryptic name will be reported.
Exactly.
I want to throw some like general knowledge out there. That is a very simplistic framework, like the left side of the brain, the right side of the brain. The way we're seeing it now is that there are four cognitive systems. There's social system, linguistic, algebraic, and geometric, like reasoning, like the four different minds, let's say. And also the way humans, the way that we solve problems, the way we reason actually is we build models of, hypothetical future possibilities of things happening. It's just something interesting, I wanted to add to our, everything.
Thank you very much. It could be potentially interesting if we decide to extend the model to other data types, like maybe texts, images. Yeah, thank you for the comment.
Have you thought about causality and under which conditions you could say that the model creates causal explanations?
Yeah, I mean, I think that's a very natural way to go with this model. We haven't done any research into that at this point, but there are methods like causal decision trees that seem, somewhat related. It's a tree-like structure which you can extract causality from. I actually don't know too much about it, but it's, there's potential for that type of methodology to be leveraged within a system like this.
Discrete systems like computational systems, like machine intelligences, they don't have a sense of, they don't have a temporal sense. So this idea of like the cause and effect, they don't understand it in the same way that we do, which is interesting.
But potentially, if we incorporate these somehow into logic, then potentially machine can do it. Like, I mean, we can, if we can model it logically, then like, why not?
It's a very tricky.
Yeah, maybe I have not thought much about it.
Yeah.
Thank you.
It's good. So this is actually great that that Git does it out. That Git selects features like out of the box, because especially like for house price data set. When I deal with it was like problem that like essentially two features were like useful and all the others they like didn't help to produce to like very model. And like, is it, since the activations essentially are defined, is it like focused to outliers? Like, does it have any like help to deal with outliers?
It's a good question. You mean outliers in like your sample?
So I haven't seen like how to define activations. So since they are predefined here, maybe they can help like to deal with outliers and just the question.
Yeah, we haven't done any experiments around that, but the activation functions are, yeah, we can pull it up here. They're clamped between 0 and 1, which means if you get really extreme values that are produced by some input, they're actually capped at how much they can influence the network overall, which I can imagine might have some impact on outliers and being robust to them. But again, we haven't done any of that type of experimentation, so I don't know.
I'm just asking because there are like also like Bayesian approach, and because of something like as outliers excluding out of the box. Here it's like selects the features out of the box.
Yeah, these are conjunction, disjunction, activation functions. So this F function on the very outer part is clamping between 0 and 1.
Just coming back to the you model with your network kind of pattern matching what I see here. The question is, have you tried to train it on maybe synthetic function to see how good it learns interrelation between features? For example, if you say, I want to learn sort function on all features, how long does it take the model to learn this function? Have you tried this?
We haven't tried that. I think that was one of the approaches we were thinking about when evaluating the explanation quality and the quality of the rules, to use kind of synthetic data where you have some expectation of what the rules should be that you learn from this data. But we haven't.
I'm just curious about the size of the model in terms of complicated functions. Do you understand?
Okay. I think if we did any experiments that might have addressed that. I think we also did another experiment where we just increased the overall number of features, so important features and unimportant features. And again, looking at like different scales, right? To see if you just add tons of features, which maybe is some proxy for complexity of the function that you need to learn.
No. Actually, there's a difference between if you just increase the number of features, but your function remains simple. For example, if you have, for example, feature number 1, number 2, number 3, number 2, number 3, number 4, or number 3, and so on, it's quite easy to learn. If you have some kind of more complicated functions that encode more interrelations between all the features, it can be just relatively small amount of features. The circuit size will be very, very large.
Yeah.
So I'm curious.
Yeah, I understand
what
what you're asking. We haven't done an experiment that directly address that. Yeah, it's a good one.
I'm trying to educate myself a little bit. So, like, how would you differ this from, you mentioned the O1 model, but like some of those are like 5.3 where it's trained on a bunch of text. Like, where do you see those playing a role versus, I guess, your research would seem a little more robust than just building up a neural network with the logic built in?
It's an interesting comparison. They're quite different, right? Like, if you think about what's happening in O1, no one really knows, but maybe it's something like, you know, was described where we're evaluating all these possible futures, and then the LLM is kind of reasoning through those different solutions to the problem and selecting ones that it thinks are promising, you know. At the end of the day, that's still all driven by an LLM that, you know, it can hallucinate on every one of those steps. We're not really able to inspect it or have any guarantee that the logic that it's using to arrive at its conclusion is the one that we would want it to use. And so I think that this type of approach can potentially be leveraged in a similar way to reason over many potential solutions in that context. But you might also get some other interesting properties, like the explanation or the reasoning being logically sound. You're obviously able to inspect it using the explanation. So they're quite different. We haven't done any kind of research into how this could be leveraged in that kind of context.
Sort of in that same vein, that idea of zooming in on the features of interest. And this is also me educating myself. Other than that sort of calculus variation and the elimination of various, how you guys are getting at, is that the primary way you zero in on a feature of interest or understand the importance?
So was the question about how we calculate feature importance or during the training process? How? important features are identified.
Sorry, no, maybe that wasn't clear. So in this process, you were talking about eliminating features. You were talking about attempting to understand which features were important, right? So in that process, you talked about elimination, and you talked about changing the weights on the features, or sorry, the nodes. Are those the primary ways to zero in, I would say, eliminate uninteresting features, or what methods do you use? And that's the rest.
Yeah, that's the whole mechanism. If we go back to the training diagram, we're basically combining gradient descent, which is updating the weights on every node within the network, but obviously also the features as well. And that gives us some indication of how useful that particular node is for making predictions. And then the bandit learns this policy over the whole of the training process to basically identify the distribution over the predicates or the features that are most useful in this particular data set.
So my question was essentially, what was the paper you wrote?
Yeah, no, I mean, it's a good question because this is a complex process and it's not something that you typically see with a neural network. And part of it is because of the fact that each of the nodes in this network actually represents a logical operation. And like I mentioned, you can't just build a fully connected neural reasoning network. It wouldn't make any sense.
What's the function of the bandit? The bandit, what is the bandit?
Yeah, so again, the bandit is basically learning this distribution of feature importances. You can think of it. And then we're going to sample from that bandit as we progress through the training process to replace unimportant kind of sections of logic with new logic that helps us make better predictions on the next iteration.
I might have missed this earlier, but how are the predicates being defined based on the features? Like, are you defining them at the very beginning, or are they actually being also trained as part of the algorithm? Like, I assume the predicates are like noise excluded and some value, or like.
Yeah, they're just defined at the beginning before training.
Oh, so let's say if I have some simple data set with some continuous features, you would just bucket them into different sort of thresholds, or would that actually happen automatically? Like, for example, in a random forest, you would split it based on, do splits based on like minimizing the losses.
Yep. Yeah, that's a great question. So we actually experimented with a couple different variations of that. So one method of binarizing continuous features is to essentially just use a decision tree, right? So upfront, you use a decision tree, you break out those continuous features into different bins, and those can become your predicates. That actually works quite well in a lot of cases. We can also actually pass continuous features into this model directly, and they just take on a little bit of a different interpretation, right? So let's say that we had a feature that was, the number of bedrooms. And this is a number between 1 and, I don't know, a mansion with 50 bedrooms. And so as 0, we're going to scale this feature to be 0 to 1 in order to leverage it within NRN. And then if we see a 0, then that basically means that the truth value for the number of bedrooms on this sample is very low, right? It's not true that this has a lot of bedrooms. This particular sample has a lot of bedrooms. If the value was 1, it would mean it is true that this sample has a lot of bedrooms. So you can just interpret the predicate in a slightly different way.
Got it. Thank you.
Actually, yeah, I want to ask a related question. As for the feature with numeric value, let's say the size of the house. So it can be from like 10 to like 5,000 square footage, and you might break it down. And then based on your experiment, is there any rule of thumb, like how, if you break it down per bucket, you have more features, right? And then that probably gonna make your model more complicated. But if you have less bucket, maybe the feature is quite not informative. And so just want to understand your experiment on that.
Yep, yeah, that's a good question. So you can just treat that binarization, if you use that method, as a hyperparameter, right? To decide essentially, how complex do you want to make these binned features? And it just, it's probably different for every problem, how complex you need that binarization to be.
Just want to confirm, no matter what is the value scale, everything has to be from 0 to 1 after pre-processing.
Yes.
Have you put any thought into implementing this type of technology to work with pre-trained neural networks?
Thought, yes. We have not done any research towards that.
I also have a question. And you showed the table where you compared your model with state-of-art algorithms, and I'm curious, what about like sample efficiency in the model? For example, like we know that neural nets are very powerful, but they are like very hungry for data, whereas linear models you can accommodate on much smaller data sets, and they are interpretable. So if I want to apply kind of use your model to the case when I don't have big enough data set, maybe just a couple thousand of rows, if it wouldn't it overfit this data?
Statistics in terms of number of features and number of samples.
Basically,
so these are our 22 data sets. As Steve mentioned, we did not come up ourselves with this set of data sets. We just took it from what other paper used, and you can see here on what we tested in terms of number of features and number of samples. The minimum one, about 5,000 or even 2,500. And I think we have performance per data set as well, right?
Mm-hmm. Yeah.
I remember it is, for example, this data set 44091. 44091. Okay, it has pretty decent performance comparisons.
Yeah, so it looks like if you look at this row, RNRN performs a little bit better than MLP. So it's maybe not the greatest example of what your question is getting at, but yeah, this is over a variety of data sets.
It's actually very interesting because some of the applications of machine learning are within their use case when you don't have a really big data sets, especially outside of the big firms that have budget for big data. And when you don't have big data set, you usually stuck with more simple models, or you have to do a trade-off between explainability or their performance. Mm-hmm. And it looks like the neuro-linguistic approach can take the best of two worlds in a sense. So yeah, good. Any closing question? Then the last question: if, for example, I want to apply, I have a machine learning problem and I want to, implement it, can I reach out to you guys and for your help to kind of build this like explainable model.
Yeah, and then also in the slide deck here, we have a link to this torch logic repo. This is an implementation of this exact approach, and it has a kind of scikit-learn type of API that you can use to train the system. There's also some tutorials in there showing how you can train, binary classification, multi-class. So there's a few different notebooks you could take a look at. But yeah, feel free to reach out to us.
Thanks.
And feel free to provide any feedback. If it doesn't work, or if it works worse than, I don't know, random forest, linear regression, whatever you try.
All right, cool. That's good. Thanks.
Thank you.
Yeah, I think you guys are gonna stick here for just a little bit. If you want to have like additional questions, feel free to grab those guys through things. Yeah, that's awesome. Everyone, let's use. So yeah, thanks again, and I think with that we'll conclude our today's meetup. Quick reminder, reminders first. We're gonna have a working session on the multimodal AI next week, and maybe we can do like a working session probably next year on the Neuro-Symbolic things. So let's join the Discord and.
Will it be recorded this one?
Yes.
What is the YouTube channel you're putting on?
Sorry?
What is the YouTube channel you're putting on?
We are in the process of migration from one YouTube channel to another one, so I want to kind of aggregate all the videos from previous meetups. It's kind of a little bit shame of us that we have not posted, even though like we're recording it. So, but we'll get there. After this event, we can like go to the bar. If someone wants to stick by, please. Here's a QR code. It's Old Town Bar, a few blocks away. You can be here, and thanks again.